And I had to write omit next to the questions, where we haven't covered the material yet. But I wanted you to get comfortable with what an AP exam looks like. How many multiple choice there are, where you can use a calculator, when you can't use a calculator. Just stay comfortable. Now, this is nothing that you're going to hand in at the end. I am going to give you the answers on my e-board. I'll post the answers. It's just too much to copy. The other thing you could do is you could just get the Princeton review book if you don't have one already, and you could look at all the explanations and answers also. Then after the break, I'll just pick a few random questions and make a test out of it. Isn't that a good idea? That way? Yeah, or if I can make change. Like, I don't want kids memorizing the answers and having no clue what they're doing, but yeah, like really simple unless like I change a 2 to a 3 or something like that. So it'll get you comfortable, it'll make you face because it's a long exam. It's over 3 hours long. There's 45 multiple choice questions, 6 free response questions. And when you're doing it, try not to use a calculator on the no calculator parts. Well, they give you for the no calculator multiple choice questions about 2 minutes a question. For the calculator multiple choice questions, about 3 minutes a question. And the free response questions, about 15 minutes a question. So it's very long. So anyway, I just wanted I thought this was a good time. There's no pressure on you, but I really want you to, start getting excited about it and see what, face it. So anyway, so for the do nows today, the first one, I want to see how you are with the disk method. That's what we were working on yesterday. You're going to get the volume of a solid of revolution. So go ahead and do that. Once you set up the integral, either do it by hand or put it into the calculator to get your answer. And the second do now we'll talk about in a few minutes. But first do that. I'll come around and check. You had to do, which problems did you have to do last night? Yeah, how many were there though? Two. Okay. Let's see. First now. Oh wait, did I not reduce it all the way? No, 5 isn't going that way. I'm getting something different. Why? You got 256 pi over 3. Maybe this is wrong. You got what I have here? Ooh. All right, let's go through. We'll see. So we have the area enclosed by a parabola and the line here. You didn't square the radius. Oh, so many people do that. That's why I like to set up the parentheses and put the square there right from the beginning. So that's so easy to forget to square the radius. Yeah, and then there's, so if you were to take this region, revolve it about the x-axis, and take a slice, it'd be a disk. The thickness is dx. Every time you go about the x-axis, thickness is dx. The limits of integration, smallest x to greatest x, would be -4 to 4. And the radius, we're going to use y top minus y bottom. So y on the curve equals 16 minus x squared. Y bottom 0. That's the setup. So then if you put it into your calculator, that's what you would get. If you wanted to actually square it out, square out the 16 minus x squared first, and take the antiderivative. Put that up there. So yeah, you could square it out. Take the antiderivative, plug in the upper, the lower, and subtract. You're going to wind up with that 16,384 over 15 pi. So either right. Question. So anyone else getting that? Just one person had a couple people? All right, I'll take that. That's good enough. So, do you see where you made a mistake if you didn't get that? No? Did you set it up right? Do you have the radius of 16 minus? Oh, you do? Okay. Oh, I thought you said no. Okay. Yep. Okay. So that's the disk method, and and every slice is going to be a disk when the region is totally connected to the line you're revolving it about. Right? Then you're going to have a solid slice. But today we want to talk about, well, what happens if each slice has a hole in it, if each slice is a washer. So, yeah, it's going to happen. That's why I have for the second do now. I want to figure out what the volume of a single washer will be, because then we can just add them up by integrating. So let's say we have a washer. I made it a little tall, which is just, it's like a cylinder with a hole in it. And you want to get the volume of it. And let's say that the radius of the entire washer is big R, and we let little r be the radius of the hole. What can we do to come up with the volume of the washer? No, like we want to get rid of, we don't want to count that. We just want the volume of the solid. Yes, ma'am. Well, before we even integrate to add them up, I just want to get the volume of one single washer. Like, in other words, like, can you tell me what the volume of the disc would be if the radius is capital R? What is it then? Well, what do you have to get the volume of the washer? You'd want to get the volume of the disc and subtract the volume of the hole in there, right? So you'd want to take pi r squared, times thickness is dy. That's the volume of the disc. And then what would we subtract? There we go. Pi small r squared times the thickness. Volume of the disc minus the volume of the hole would give you the volume of the washer. Well, you see how each of these two terms has a common factor of pi in it? We could pull the pi out. Now, we could also pull the dy out, but we don't want that in the front. So I'm going to pull out both the pi and the dy, but I'm going to pull the pi out front, and the dy, I'll pull it out in the back there. So it'll look like pi, and we have the r squared minus little r squared, the dy here. That would be the volume of that one washer. You see how I did that, guys? If you distributed the pi back and then you distributed the dy in, you'd be right back here. So let's say I have a washer and I just turn it a little, so now the thickness is a small change in x, it's dx. What do you think the volume of that washer is going to be? Same thing, just dx. So it's pi 3r squared minus little r squared. Yes. Okay. So you know we don't care about just the volume of one washer. We want to add up an infinite number of them to get the volume of a solid. And that's what we're going to do today. So basically we'll have these formulas with just an integral sign in there. And I had some cool apps to demo this, but they don't work. But I do have a quick little movie. It's not as good, it's not, but I'll just to get the idea. And then I'll fast forward it. She'll turn the sound down.
Volume count.
Oh, no, please get it. Okay, with the disk method, if you have a region, I'll go back here. See, if you have a region and you revolve it about a line that it's attached to, here, oops, you get a solid, but every slice is a solid disk. You see that? That's what we were doing yesterday, okay? Well, let's say now, though, I just wanted to show you, so every slice is a disc. That's what we did yesterday. But let's say, he does a few discs. You don't care about that? That's disc. Oh, it's coming right up. Come on. Okay, right there. Close. All right, now let's say we're going to take this region enclosed by these two graphs over here, and we're going to revolve it about the y-axis. And then we're going to take a slice. That slice is not going to be solid. There's going to be a hole. If there's a space between the region and the axis of rotation, then the slices are going to have holes in them. They're going to be washers. Can you picture what it would look like if you take that region and you spin it around the y-axis? Nope. Can't. You can't. That's it. You can't. That's the answer. Let's see what that's going to look like. So we're going to go about that axis. Come on. Look at that. Oh, cool. Now I see it. And if you take a slice perpendicular to the axis of rotation, come on, slice it. Ooh, that slice looks like a washer. Right? And the idea is that we can just add them up, in this case, bottom to top, and we'll have the volume of the whole solid. So, that's with a little demo. I would just back to this thing. Yeah, feel, if you're bored at home this vacation, if you go to the website, did I give you these or no? On your notes? Oh, forget it, you can't. If you actually Google Larson, Larson, calculus applets, you can actually get some where you can control them, and it's really neat just to see it. Larson. Oh, I have to go over these two homework problems. Okay, so before we start in with the washer examples, number 4, let's check the homework. 125 pi over 3. Is it 4 one of the ones you had to do? Really? How'd that work out for you? Nope. 4. You got a negative answer? Oh, man. Oh, that's awkward. Well, first of all, check. Are your limits of integration 0 to 5? Okay, you got a dy, right? The radius was the x on this line. You had to solve for x. It was 5 minus y? Really? So just square it out? Okay. You took the antiderivative? Really? Minus 5y squared plus 1/3 y cubed? You plugged in the 5, you plugged in the 0, you subtracted. Really? Can't believe it. Well, when you put the 5 in, so the first two terms knock each other out. So you only have the last term. 5 cubed is 125. That's what I'm thinking. All right, what about the rest of you? Questions on that one? So, yeah, we're going on. All right, so here's the problem with the 5th one. A lot of you looked at the graph and you didn't see that y equals x cubed actually intersected with the line x equals 8. It just did it really high. So if you just look on like a zoom 6, you're not going to see it. It goes way up to 8 to the 3rd, But you had to know it was going to intersect somewhere, right? No? Just gave up? All right. No! I do that, but wasn't this time. So yeah, this time, this region here I've outlined in green about the x-axis, so each slice has a thickness of dx. The radius, distance from the axis of rotation to the outside of the shaded region, y top minus y bottom, that was just x cubed. And limits of integration, since it was dx, 0 to 8. And it came out to be that really crazy large number. So I did see quite a few people had it, but I think a lot of people that didn't have it just because you couldn't figure out what region were they talking about. Questions on that one? Yeah. Okay. Okay, well, first, okay, so you're saying, like, you see how to get the region, okay? Mm-hmm. Oh, okay, this is how you know. Whenever you go about the x-axis, your slices always have to be perpendicular to the axis of rotation. So they have to go this way, okay? So the thickness is a small change in x. So if you draw them this way, then you'll see that the radius, it has to be the distance from the axis of rotation to the outside of your region. There's just going to be and if it's a vertical distance, you got to start with y top minus y bottom. Get that length. Yeah, that has nothing to do with the radius. The x equals 8 comes into play when you're looking for your limits of integration. Or you look for the smallest x to the greatest x. Yeah, correct. Yep. Well, does that affect the radius of any single one of these discs in here? That eight over there? No, because all you have to do is represent the radius of a disc placed in this region going across. And this distance here has nothing to do with that 8 over there. Okay? You're welcome. Okay, so let's have some fun with this washer method. This new method, when the area is not attached to the axis, you're going to have to use the washer method. So let's sketch this one. You guys know what the square root of x looks like? All right, that's good. Looking good. I'll just say yes. What about y equals 2? What kind of line is that? Horizontal. Love it. Okay. So this is a 2 here. X equals 0. Y-axis. Good. So does everybody see what region is enclosed? Okay. So we have to identify the region. No, it's not you. Somebody who's not here. Sydney, what color do you want? Oh, okay. You know what? We'll go as close to red as they have. This is like close to red. Yeah, the custom color. I guess I could have done. Ooh, oh. This is not going to be good. I can see it. It's too thin. I can't do it. Sorry. Yeah, I know. I know. I just didn't want to. All right, now I need you to use your imagination. I need you to tell me what this is going to look like when you take this region and revolve it about the x-axis. Like an upside down what? Crown. If you're looking at it from the outside, let's say I'm holding this. Let me just draw this other side. Oh, that's bad. If you're holding this, it looks like a cylinder from the outside, like it looks like a can. But then when you look down, you look at it, oh, it's going to have a hole in it, right? You have a garbage can like that? Have you ever seen certain kind of, have you ever seen maybe in your parents' cabinets, they might have little glasses? Certain little glasses, they might look like that on the outside, but on the inside they're scooped in. Shot glasses. You know what I'm saying. I'm trying not to say. Look at all the kids are like, oh, now I know what you're talking about. What's that? No, I'm just like, what is this? All right, back to the back. No, sometimes they look like that. On the outside, they look like cylinders, but then they're like scooped in. The hole is like that. So let's. I was just asking about you the other day. Hi, calculus now. Were you all that tatted up before? Oh gosh, can you erase that?
Yeah.
How are you? I'm recording. Let me just. All right, let's draw a slice. Our slice, it's going this way. No. Oh yeah, the axis is this way. You're right though. The slices go that way. Now when you draw it, I'm saying you can draw any slice you want. This is how you do it. You draw. It's nice seeing you. You look great. All right. You draw one circle from outside to outside. I'm like, if you revolved it about that line, that would be like what you see on the other side. It's coming out of the board. It's going into the board. We're trying to see what a slice is going to look like. You'll see it when I'm done. All right. We're going about the x-axis. Now, you're going to make another oval from inside to inside. This is, I really want to do a good job with this. Now, here's where the artistic effect comes in. What you do, like remember with the disc, we followed the outside to make it look like it had a little thickness. Okay, that was cool. But this is, Cole showed me this last year. You got to follow the opposite side on the inside, right? I see it. Do you see it? Oh, a kid from last year. He told me that because if you follow the inside on the other side, then you get that whole 3D effect. Wow. Cool. You see it? Yeah. Well, now you got it. Yeah, each slice is a washer. You want to think of a donut? All right, let's write this out. Now, for the washer method, remember we have the pi out in front. We're going to integrate, it's not just r squared, it's big R squared minus little r squared. So we're going to have two radii to figure out. And then you're going to have to figure out whether it's dx or dy for the thickness of your washer. Dx, and anytime you go about the x-axis, it will be dx. Dx. Fun. See, I'm setting up my squares. I don't want to even think about forgetting them. Now, big R, that's the radius of the whole thing. That's the distance from the axis of rotation to the outside of the shaded region. All right, that's this distance. I'm going to label it here. So it's that whole distance from the axis of rotation to the outside. What do you think that's going to be? Think of y top minus y bottom. 2, right? It doesn't matter where you draw your washer, big R is 2. I'm going to do it in blue because it's going to do that. Oh, but now it's in the way. Okay, I got to move that over so you can see. Little r is the radius of the hole. So it's the distance from the axis of rotation to the inside of the shaded region. So you always start at the axis of rotation, but little r, the radius of the hole, you only go to the inside of your shaded region. So that's radical x. Because it's y top is radical x, y bottom 0. Now we need the limits of integration. We want to add these up from the smallest x to the greatest x. What is the smallest x of our shaded region? 0. Now the thing is, I want to go from here to here. I know the y coordinate of this point is 2, because that's the line y equals 2, but I need to know the x coordinate of that point. How'd you get that? Oh, yeah, that was good. Yeah. Okay, and you can set y on 1, which is rad x, equal to y on the other 2. Square both sides. You get x equals 4. So that's the point 4, 2. So limits of integration 0 to 4. Now, since your regular homework is going to be to finish these, I think we should, instead of me finishing this one out, I know you can do that, why don't we set up another one? Look at the page and pick something you feel is horrible. Why don't the kids like the trig? Okay. All right, first of all, guys, tell me what y equals cosine of x. Where does it start? When x is 0, where does cosine x start? At 1, right? It starts up here and then goes down like that. We're only talking about in the first quadrant for this one. Now, sine x, where does that start? 0. 0. And that one goes up, right? This time it says, find the volume of the solid generated, blah, blah, blah. The area in the first quadrant enclosed by the y-axis, the graph of cosine x, and the graph of sine x. So you might see different regions and say, well, how do you know which one? But it has to be the y-axis, cosine x, and sine x. So it has to be this region right here. And we're going to revolve that about the x-axis. So I got to color it. Any other suggestions? Yeah, it's pleasant. It's pleasant. Yeah. All right, and oh wait, it's in here. Oh, oh, Sydney, look. Nope. Sorry. Uh, well. All right, now I don't know. I don't even know what this would look like, honestly. If you were to take this and spin it around the x-axis. Oh, yeah. And you know what? That actually makes sense. I was thinking like a volcano. Sure. Have you ever had like a pumpernickel bread and they carve out the center and then they put dip in it?
What about like a bread bowl?
A bread bowl. Yeah, like that. All right, I'm drawing in the slice. Guys, here's the fun part. You get to draw in the slice. Outside to outside. Inside to inside. Follow one side down and follow the other side down. Oh, yeah. Yeah. All right, now this time, you got to tell me the washroom method, the formula. What do I have to write down first? And it's the integral. What do we have to integrate? Big R squared minus little r squared. Okay. And then it's going to be dx again. Sorry. I know, they probably wanted one with a dy in it. All right, let's talk about big R for a second. Big R is the distance from the axis of rotation to here or up there? Up there, right? It's always to the outside of the shaded region. So it's this whole distance. What is that going to equal? Cosine x, because it's just. Little r, the radius of the hole, is the distance from the axis of rotation to the inside function. Sine x. Now, as far as the limits of integration go, I know what the lower one is. What's the lower? 0. But we're not going to our calculators because you guys know this. When these two graphs intersect, the cosine and the sine are equal. What angle? 45. Remember the cosine and the sine of 45 degrees? It was rad 2 over 2. Only we don't speak degrees in here. That's naughty. We have to speak radians. 45 degrees. Pi over 4? Yeah, because it's 180 over 4. Yep. Yes. Anytime you want to do limits of integration for any of these volume problems, first of all, look at your differential. If it's dx, you look at your original enclosed region, and you have to go from the smallest x to the greatest x. Yeah, not after you spun it or anything. Okay. All right, so the upper limit of integration now we know is pi over 4. So you could do that one, right? Maybe we could set up one more, because you could finish this one. Oh, this one, guys, you're not going to be able to do by hand. You got to do it on the calculator. You can't integrate cosine unless you knew there was a trig identity, but unless you replace this with a trig identity, you can't do it. It's cosine of something. There's a trig identity that's equal to cosine squared minus sine squared. What is it? 1 minus cosine squared. Nope. It's cosine of 2x. If you knew that that was equal to cosine of 2x, you could then integrate it. But you can't integrate these separately because you can't think of this as a u squared. You don't have a du. So unless you substitute, so this one you could just do on the calculator, unless you want to do it that way. Do we have time to set up a picture for one more? Which one? I want one where it's about the y-axis, though. 4? Bam. What does the graph y equals 8 minus x look like? No? Okay, the line y equals 8 minus x. It's a line like that, slope of -1, orange slope of 8. Y equals 8. That's a horizontal line. And x equals 8. What? So vertical line. Oh my gosh, do we see the region? Well, the one has to be enclosed by all of them. Has to be enclosed by those 3 graphs. Sorry, it's what I chose. I know you don't like it. Okay, so we're taking this about the y-axis. So then the other side, oh, I didn't leave myself enough room. Oh well, it'll be a little mini on the other side. So the slices, yep. Oh well, oh well. Okay, so you can see the disk. So let's write down the Wasserman. Volume equals big R squared minus little r squared. Oh, bless you. Big R, you're going to have to do x right minus x left is 8. Little r is going to be x on the line. You're going to have to solve for x on the line. You're going to have to see what x equals. That was whack. Have a wonderful vacation. Go over this, get comfortable with the AP exam. Start dreaming about it.